This is the pre-lab talk for Chem 110's experiment number 7, limiting reagents. The goals for this experiment are to apply the ideal gas law and stoichiometry to learn about the meaning behind the coefficients that appear in a balanced chemical equation. We also wish to achieve results that are highly accurate and precise so we can answer this important question. For today's safety pause, we note that hydrochloric acid and sodium hydroxide solutions are corrosive. We also note that some special instructions for disposing of waste. We want to make sure that we can collect magnesium, a flammable metal, in a separate waste container and neutralize any acidic solutions before flushing them down the drain with plenty of water. And of course, we'll make sure that we goggle it and wear flame-resistant lab coat. Here's a look at our experiment in context. The reaction that we are studying is the reaction between magnesium solid and hydrochloric acid in aqueous solution to form an aqueous solution of magnesium chloride and hydrogen gas. Typically, when we run this experiment, different student groups are assigned amounts of magnesium and hydrochloric acid so that either magnesium or hydrochloric acid is the limiting reagent. However, as we do a video of this experiment, we note that we can only really choose one situation. The key thing is to very accurately determine the moles of reactant and product before and after the reaction takes place and use those amounts to calculate the change in moles. Then we can study whether or not the initial moles, the change in moles, or the final moles actually correspond to the molar coefficients represented in the balanced chemical equation. As we said before, to do that, we must have very precise and accurate results. This requires 3 associated measurements. The measurement of the mass of magnesium before and after the reaction takes place, the measurement of the volume of hydrogen produced during the reaction, and finally, determining the volume of our HCl solution that reacts, which we'll do using a titration. We'll briefly talk about weighing the magnesium, which we'll do using an analytical balance that allows us to get a mass measurement that is very precise out to the 10,000th of a gram place. If magnesium is our limiting reagent, then there will be no more magnesium at the end of the reaction. However, if there is magnesium left over, it is very important that we very carefully remove that magnesium ribbon and allow it to dry before taking a mass measurement. It's also important to note that the magnesium is typically pretty fragile after the reaction takes place due to its surface being eaten away by the hydrochloric acid. So it's very important that we keep all pieces of the magnesium together to get our weighing. The second thing that we need to know is the amount of gas that's collected. Typically, we run reactions in open containers, but this time we want to actually collect the hydrogen gas that's produced. We use a new technique, collecting a gas over water, in which the gas is funneled through a filter flask using rubber tubing into a graduated cylinder that's opened on the bottom. The gas pushes the water out of the graduated cylinder, and we're able to measure its volume. Of course, the very important part of this is that we have to get the graduated cylinder completely filled with water inverted into the beaker of water. Spoiler alert, this takes me 3 tries during the video. So it's usually important that we be pretty patient. It's important that I also show you that process to show that, just because you're a professor doesn't mean things always go easily. To determine the moles of hydrogen gas that's collected, we need to use two different empirical gas laws. The first is Dalton's law of partial pressures, which states that the total pressure of a gas mixture is the sum of the partial pressures of all of the gases in the mixture. We note that in this case, and in any case of collecting a gas over water, that the total pressure will be the sum of the gas that you're collecting, the partial pressure of the gas that you're collecting, plus the vapor pressure of the water. We note the lab temperature and the vapor so that we can determine the vapor pressure of water by looking up that value in a table. And we measure the atmospheric pressure on the day that we do the experiment. This serves as our total pressure. Therefore, we use the equation on the top of the picture to solve for the pressure of hydrogen gas. We can use this pressure in the ideal gas law, which is below the picture, PV equals nRT, along with the volume of hydrogen gas that we collect and the lab temperature, to calculate N, the number of moles of gas that is produced in the reaction. Note that the R that we use in the ideal gas law is 0.0821 liters times atmospheres per mole times Kelvin. Our final measurement is finding out the amount of hydrochloric acid. To make sure that we achieve a very high precision on our volume measurements, we'll be using a burette to deliver the starting amount of hydrochloric acid that will be used in this experiment. We also note that there are very precise concentrations of both our hydrochloric acid and our sodium hydroxide that we'll use in our calculations. To figure out the amount of hydrochloric acid that is remaining after the reaction takes place, we titrate it with sodium hydroxide. It's very important to note that even if the magnesium is in excess, meaning that hydrochloric acid is the limiting reagent, we still do a titration because oftentimes a very small amount of the limiting reagent is left in solution. However, it is extremely important that we do the titration if magnesium ends up being the limiting reagent. So how do we set up our titration? The first thing we do is take our filter flask and add 1 to 2 drops of phenolphthalein. Phenolphthalein is an acid-base indicator that changes from colorless to pink in the presence of excess base. We need the phenolphthalein to determine what the endpoint of our titration will be. Also, it is really important, since we don't know how much hydrochloric acid is remaining, to titrate pretty slowly so that we don't overshoot our endpoint. As we titrate, we'll swirl the flask to ensure the proper mixing of the reagents. And finally, we end our titration when a permanent pink color exists in the flask. When we do our titration, we note that hydrochloric acid and NaOH react in a 1-to-1 ratio. Sorry about the mistake on the products. That should be water at the end. Therefore, if we know the moles of sodium hydroxide that we add to our solution, then we can figure out the moles of HCl added using the 1-to-1 molar relationship. You'll see in our experiment that once we know the moles before and after the reaction takes place for all of our products and reactants, we can put them together in what's called an ICE table, or ICF table, I guess in our case, where we track the initial, final, and change in moles. Therefore, then we can compare different amounts to determine which ratios match the the coefficients in the chemical reaction best. Okay, hope you guys have fun with this experiment and watching me make watery messes.